Hello, and welcome to Palisade Corporation's Webcast, DFSS-based design optimization using design of experiments and at risk. Presented by Jeff Slutsky, Bausch & Lomb's Worldwide Director of Design for Six Sigma. My name is Jameson Romeo Hall, and I will be your host today, and I will be available to help answer web technical questions by chat. If you experience technical difficulties joining this WebEx session, please dial 1-866-229-3239. Alternately, you can email technical questions to support@webex.com. At this time, all attendees are in a listen-only mode. Please note that as an attendee, you are part of a larger audience today. The attendee list is suppressed to maintain attendee privacy. We will be holding a Q&A session at the conclusion of today's presentation. You may ask an online question anytime throughout the presentation today by clicking on the question mark icon located on the floating toolbar in the bottom right side of your screen. We invite you to sit back and relax and enjoy today's presentation. I would now like to introduce your presenter, Jeff Slutsky. Jeff, in a minute or so, you will now have the control.
Okay, thank you, Jameson. Yep, share application, okay.
Good. Did you click the share desktop? Oh yeah, we're in good shape.
Okay, for all attendees, you should see the introductory slide to the PowerPoint presentation, slide number 0. So first of all, welcome all to this webinar from far and wide, to some good morning, to some good afternoon, to others good evening. I understand we have somewhat of a global participation this morning. I'm located in Rochester, New York, and so it's a little after 11 a.m. Eastern Time for me. What I'm going to take us through is the use of some of the DFSS tools, primarily for characterizing the behavior of a system and then optimizing that behavior. So the primary tools we'll go through are design of experiments, and then Monte Carlo simulation and optimization, the latter two facilitated using the at-risk software. A little introduction to myself. I'm Director of Design for Six Sigma here at Bausch & Lomb in Rochester, New York. We are an eye care company. We manufacture pharmaceuticals, medical devices, and probably most notably contact lenses. Design for Six Sigma began here at Bausch & Lomb in about 2004 when I came here to work as director, and been spreading it since globally, Munich, St. Louis, Rochester, New York, and so on. And the DFSS training that I conduct here for Bausch & Lomb contains the use of optimization and Monte Carlo simulation using the at-risk software tools. So again, a little introduction to myself. I've had the pleasure of co-authoring a successful text, and my telephone number is lower right-hand side there. That's my cell if anyone would like to get in contact with me directly. So getting into the flow, first of all, I'll go through the steps that we're going to go through in this presentation. So initially, define the system to be developed. This is designed for Six Sigma, and so the assumption is that this is the development of a new product or a new process as opposed to the optimization of an existing one, which would be more the domain of Six Sigma. So define the system to be developed and model the system from first principles of physics. All of this simulation and experimentation and empirical modeling, design of experiments, it's all great, powerful, useful tools, but ultimately you must hang your hat on some amount of understanding of the first principles of physics. If nothing else, to judge the quality of the models you're creating to describe your systems. Of course, then design the system and eventually build a physical prototype of the system. Run a DOE, a designed experiment, on the prototype from which to get an equation which describes the critical responses of the system as a function of the critical parameters, the critical inputs, y as a function of many x's. This equation augments the information we would have from the models created using physical laws. Next set of steps would be then, again, the transfer function created from the design of experiment, the data generated in the DOE, and use that transfer function to optimize the response. In other words, find the values of the x's that place the response on target, and then with those optimal values, use Monte Carlo simulation with knowledge of how those x's distribute themselves statistically to predict capability of the responses and therefore of the design. And probably most importantly as a final step is to confirm that all this work that you have done, which is primarily computer simulation and mathematics, confirm that all that modeling and simulation in fact does adequately model the system. So compare or confirm simulated performance with actual performance. You should be looking at slide 4 now. So the example here is that of a medical device used to identify various microbes in a sample of human serum, 100 microliters. This was work done at a previous company that I was with, and it was DNA testing was the basis of this. So the things we were looking for in the blood was anywhere from pneumococcus bacteria for pneumonia to being able to identify an individual by a sample, kind of a CSI crime scene type of application. Part of the functioning of the system, the way it replicated the DNA of the microbes in the sample was to repetitively heat and cool the sample. Heat to 90 degrees using resistive heating, cool to 30 degrees C using forced air. And during development, we had a very small thermocouple available and placed inside that sample so we could measure the temperature of the sample, human fluid, human serum, inside that little pouch, the sample pouch. So critical response, several critical responses of this system. One was the time it took to cool the sample from 90 degrees to 30 degrees C. And the requirement was 2 seconds plus or minus 1 second. There were 5 critical X's, critical parameters of that critical response, cool time, 5 critical parameters that affected cool time listed here. This was forced air cooling, so there was a fan whose speed we could vary that would cause the airflow. Also, the amount of fluid in the pouch was believed to be a significant contributor to the cool time. And the ambient conditions of temperature, altitude, and RH were suspected to affect the cool time. temperature and altitude believed to be more strong in effect than RH. Obviously, if you're cooling this to using forced air, the initial temperature of that forced air has an effect on how quickly you can cool, and ambient altitude really has an effect on how much heat the air can carry away, can transfer. And the limits, the ranges within those within which those X's were investigated, shown on the right. So a couple of famous dead guys invoked or reincarnated somewhat to understand the physics of this system. It's important to go back to the physics of what's going on, or whatever the first principles domain is appropriate, chemistry, physics, whatever it is, and try to find out what are the ideal functions, the ideal equations that are operating in the system to understand how the system should behave. And Fourier and Newton provided some help here. Carl Gauss is involved a little bit in terms of normal distributions and so on. But from these laws, from these relationships, heat conduction, laws of heat cooling, thermodynamics, we had an idea, a good idea, that the relationship between the X's and the Y, the parameters and the response, is first of all likely to be nonlinear. And in addition, some of those X's are likely to interact. And we had a very simple model of the behavior of the system. The cool time on the left, an exponential function, exponentially falling function from 90 degrees to 30 degrees with a particular time constant. And then when the resistive heating was turned on, a much shorter time constant, but exponential as well, for the time to go from 30 degrees to 90 degrees C. So here was a little bit of the math based upon first order differential equation based on thermodynamics and heat transfer. So we had an idea of how the system should work and what are the things that should drive the time constant and the initial and final values of these curves, and their, well, time constant is essentially equivalent to their times, the fall time and cool time and heat time. So with that knowledge, an experiment was designed, and the experiment was chosen such that it could estimate the linear, nonlinear, and two-way interaction effects. Now, I apologize if I'm using terms with which some are not familiar. I know I'm mixing design of experiments with optimization and so on. But for those who are, probably have an idea what I'm talking about. The type of experiment run is tightly linked to the type of information you need to get out of that experiment, the type of equation you want to build. And so it was the first principles information on the previous slide that helped us understand what kind of equation we would need to build, or also called a transfer function, and therefore what type of experiment we would have to run. At the bottom left, you see a note that a central composite design was run. We ran it in an environmental chamber so that we could vary those ambient conditions, temperature, humidity, altitude. And then there's a very powerful and commonplace software tool, a statistical analysis tool called Minitab that we use to analyze the data and from which to create the transfer function that related the X's to the Y. On slide 9, you see a little screen capture from the Minitab software output. And basically, I just call your attention to the item in the red box. That is the equation built from observed data that describes cool time of that system. So you can see that the fan speed, no surprise, is a important factor. The volume of serum in that sample is important. More volume requires transfer of more heat. The ambient temperature, and in addition, due to some physics, to the fan laws, the speed of the fan squared was an important driver to cool time, as well as an interaction between speed and volume, the fan speed and the sample volume. So that's the equation describing behavior. And if I go back a slide to slide 9, the important thing to do at this point would be to choose values of speed, temperature, and volume, calculate the cool time that you would get, and then run the actual system that way and confirm that this equation is adequately modeling the physical system. Assuming that's the case, we can now search for X values that place that Y value on target. Now, this example, the equation is not extremely complicated, and one might argue could even do it by hand, some differential equations and so on, but it's a lot of work. It makes more sense to use some software package to do that, and I chose at-risk optimizer for that. So step is create an Excel file that contains that transfer function in it and the range for the X's over which to do the optimization search. Of course, then open up the optimizer and run it. So if I get out of the PowerPoint and into the Excel, you'll see from, I hope everyone can see the Excel file, and I have the at-risk optimizer and the at-risk Monte Carlo simulator running.
Hi, Jeff.
Yes?
I'm not sure I can see it. Let's see. Got it. Thank you.
Okay. Thank you, Jensen.
Thank you very much.
Thank you. So you'll see two halves, two pieces to this Excel. The first one in B2 is optimization. The second half begins in B14 for Monte Carlo simulation, MCS. So it's somewhat of a two-step process. First one being optimization, second one being the Monte Carlo simulation to predict capability. So dealing with the first half first, you can see the factors, speed, volume, and temperature, and in addition, the squared effect of speed and the interacting effect of speed and volume. The numbers listed in the coefficients column are the coefficients of that transfer function we saw earlier, and these are the first guesses at the values for those three factors, speed, volume, and temperature. And then above in E3 is the constant for that equation, and then below are the products of the coefficient times the factor level. And further to the right in columns F and G are the limits for speed, volume, and temperature. Speed is in RPM, volume is in microliters, and temperature is in degrees Celsius. So the use of the optimizer requires you to initially set up a model, not to be confused with the model we're simulating in the Excel. And here I'm telling it that cell E11 is the quantity to optimize. It has a target value of 2, and I'm interested in the mean. You can see that there are other criteria, other metrics of that response that could be optimized. I'm interested in the mean. And below adjustable cell range, excuse me, I'm telling at risk what are the limits for each of these three factors, so the 300, 1500, 50, 150, and 15 and 27 degrees. And say OK. and then I'll run the optimizer with the default settings for the optimizer. And a nice little tool is shown down here, the watcher, which allows you, I'll move it around a little bit, which allows you to watch the progress of the optimizer. And those lines should slowly converge on a number very close to 2. And you can see the factor levels in D5 through 9 changing. So it's...
Hi, Jeff.
Yes?
We actually have the spreadsheet up, but the optimizer window is that.
You don't...
It's grayed out, outlook.
You don't see that?
Now, Jeff, are you sharing desktop or are you sharing your application?
You know what? I must be sharing application because you're only seeing pieces. Is that correct?
That's correct. That's correct, yeah.
Okay.
Sorry about that, everybody.
Sorry about that.
All right, I need to get back to... so the window I see is...
But we're good so far.
Okay, just you can't see everything at once, I guess, is the...
Right. I guess if we switch back to share desktop, we'll be all set. Even if you...
Okay. I think I have to get out of exit sharing to do that. Is that...
Yeah, see what happens.
Share desktop. Okay, that should be better. You see the PowerPoint and Risk Optimizer Watcher?
Oh, we've got it. We've got the optimizer watcher right in front of us.
Okay.
Great.
Right, now, for some reason, the Excel is taking its time to refresh.
Not as tech science, our webinars. Well,
there we go. Okay, I apologize for all that.
That's great.
What you should see is Risk Optimizer Watcher window, and behind it, the Excel spreadsheet.
Perfect.
Okay. So the optimizer has concluded. I can ask for different reports at this time, which I'm not going to. What I do want, though, is to display the best solution found. If I say OK, I get a summary report. My interest is in cell 11, very, very close to 2. That was our target. And you can see that the values for speed, volume, and temperature have changed from their initial. We had 1,120, I believe. You can also, if I now go to the next section, which is the Monte Carlo simulation section of the Excel spreadsheet, I now have my optimal values for the x's to give me my target y. But what I don't know is, given that those x's, speed, volume, temperature, given that those x's do vary, even when set to nominal and varying around nominal, you know, what is the capability? What's the CP, CPK, the capability of the response in terms of the probability of remaining within the spec limit, 2 seconds plus or minus 1 second. So I've created the next part of the worksheet of the Excel spreadsheet. And same factors, the same coefficients. This is the factor level. Actually, it's, I believe, from the last time I ran this simulation, their product. And now E24 is now the sum of the constant, which is in E15, that has not changed, and the sum of each of these terms in the transfer function. There's also a cell in E25, a value in E25, which right now, it's not a valid number, but once we run the Monte Carlo simulation, in that cell will be the calculated capability of the system when those x's, speed, volume, and temperature, vary around their nominals. You can also see that in C30 and 31. For example, in C30, 1375.4, if I go up a little bit. So what I've done was to connect the lower part of the worksheet, the Monte Carlo simulation portion, connect it to the optimization portion so that those numbers are automatically stored or taken as the mean values for the way these factors distribute themselves. So I know that fan speed was roughly normally distributed. The mean I want that's fan speed is the mean found for optimization. That's where I want to run the system, after it's been designed. And I'm going to put in 100 here for the variation because initially we had about 100 RPM of one standard deviation of variation. The fan could run from 3 to 1500 RPM. Same thing for volume. It looks like about 72, 71 microliters is the best volume. Variation around volume based on how that pouch could be filled. Min and max, and then ambient temperature. You can see that there's ambient temperature was assumed uniformly distributed, and there's no mean value for that. So I'll change this as well. Originally, the limits were 18 to 27 degrees C. If I go back into the PowerPoint, just to conclude this section, the next step would be then to take these optimal values that the optimizer predicted and set the prototype up, the physical system up that way, and measure the cool times of the actual physical system and test whether that these optimal values determined during, basically in math, do they really result in the predicted cool times in the actual system. Again, these confirmation steps are very important to make sure you're not going off into an area that, a direction that further and further, poorly models the real system. Again, we're just doing math here. You always have to test that it's actually modeling the physical system adequately. So if all this optimization and DOE and analysis is correct, if we were to measure the cool time several times, we could create a confidence interval from those data, from those observations. And if the analysis is correct, 2 seconds should be in that interval somewhere. Obviously, you can't just measure the actual system once, get a number, and compare it to the number 2. It will virtually always be not the number 2. So a nice way to deal with that is using confidence intervals. So again, the next step would be determining capability using some metric, CPK, PPK. And the Monte Carlo simulation is a nice tool, a nice technique to achieve that. Very basically, the general steps of Monte Carlo simulation, create a parameter-based model of the system. We did that. That's that transfer function. Randomly select a set of values for each parameter. We've given it the distribution, and at risk knows how to randomly sample from those distributions. Plug them into the equation and get a solution, get a value of y, save it, ask or test if the simulation is complete. If not, continue, each time saving a solution, a predicted value, a y. And when simulation has ended, now we can analyze the statistics of that response. So those are the steps we'll go through here next, using the rest of that spreadsheet. And again, here are the assumptions around the statistics of those three X's, those three critical parameters. Normal, uniform, and you'll see opt. So this is the nomenclature here. Speed is a normally distributed random variable whose mean is the optimal value, which we don't know yet, but we do now because we run the optimizer, and whose standard deviation is shown here, so 100 RPM. So we'll go back into the Excel spreadsheet and now run the simulation. And if I move that over a little bit, you'll see the on the bottom left, you'll see the simulation proceed and conclude, and we get a distribution of the solutions for each of the 10,000 solutions that were, or values that were tried. Also, you can see a capability, an extremely low capability. This is CPK of less than 0.1. So one thing you can see from the chart, from the graph, is that the mean is way off target. It's 1.2. We had a 2-second target. I can go into the sensitivity analysis, tornado graph, got various names, and try to determine what is affecting variation the most. And in this example, from what I see here, speed is having the greatest effect on variation in cool time. So what I might do now is to try and reduce the variation in speed. So if I knew, or if I know that it's possible, for example, to reduce the variation in speed, maybe I can cut the variation down by down to 10 RPM as 1 SD using some kind of closed-loop control method. Let's see what the effect, and again, let's see is one of the great values of this tool. Let's see what the effect of reducing that variation in speed might be. Capability has improved a little bit. You can see that we're still off target. 1.1, we needed a cool time of 2 seconds. This is showing me that temperature now has the biggest influence on variability. Robust design is typically a 2-step process. The first step is reduce variability. Excuse me. The next step is place the mean on target. So I'm going down the first step now, which is reducing variability. And who's contributing most to variability now? Now that I reduced speed variation, it's now temperature. So I can go in and for temperature, try and narrow down. Again, later on, we'll test whether these ranges are possible to attain in reality and economically. But right now, we're doing the design what-if stages. What do these parameters need to be to meet what I'm trying to attain? So let's say I narrow the temperature range a lot, around 20 degrees. Let's say I narrow it to 18 to 22 degrees. Again, start the simulation and see what has happened to variation. We're outside. We've gone below, actually the capability is negative, we've gone below the target. See the 1 second, the 2 seconds is out here. At this point, what I would do is adjust the fan speed. The fan speed adjustment is there to to be the primary method of adjusting temperature, the cool time, I'm sorry. And it looks like the cool time has to be increased, which means I should run the fan at a slower speed. I'm going to try 1200 RPM. I know we're deviating from the optimal. But what we're seeing is the effect of the variation in the distribution driving, of the X's driving the Y. So it looks like I've slowed this fan down by too much. 2.6 seconds. We're over the 2. The optimal was 1375. Let's try 1300. And if this a little too slow still, excuse me, a little too fast. If this looks like a trial and error approach, it very much is. But the efficiency and power of doing it in simulation is what makes it practical. If you were to try to run this experiment each time physically, changing the fan speed, it would take a whole lot more time. So 1.7, you can see that capability has jumped a lot because we're closer to the target, 0.9. But I can slow the fan speed down just a little bit more and get closer to the 2, so maybe 1280 RPM. And the iterative process, again, 1.9, looks like about 1.9 seconds for cool time. This is not updating here. I'm looking here for the current cool time. So you can see my capability has increased quite a bit by getting closer to the target. I might look at variation now, because while my response is very close to the target, obviously there's still too much variation in the response. So I look again here to which response is driving the variation in the response. The sensitivity analysis is telling me it's still volume. Maybe I can tighten this up even a little bit more. Slightly narrower range, run the simulation. My capability has increased to 2. Distribution has narrowed. My standard deviation has decreased. Still essentially on target, 1.93 seconds. I don't think if I increased the little difference, that it would make that much of a difference in my variation. Who's the culprit? It's still volume. It's still now volume is the source of variation. So maybe I can reduce the variation in that from about 7 microliters. Maybe I can bring it down to 2 microliters. What would happen if I were able to achieve that? If I go back to the density chart, 1.9, my mean is still where I need it to be. Capability has increased, 1.8 now. My target is 2, by the way, CPK of 2, Six Sigma performance. And if I want to get higher in capability, again, it's now temperature. You can see the influences change a little bit depending upon the variations I choose for each of them. Maybe I can further narrow temperature. Let's see what we get here. I've narrowed it more than I need to. See, the capability is now above 2. So the range for temperature variation is a little wider than the 2 degrees I show here. And I may be able to play off increase or tightening variation elsewhere and then be able to open the variation on temperature. If temperature is a difficult quantity to control, maybe I control more tightly the other X's that might be more, easier to control, and open this up. But we've got more capability than we need at this point. Still about the same mean. So I might be able to open up temperature by a little bit. I think I had tried 18.5, maybe, I don't know, 1875, maybe 21.75, maybe open it up a little bit, and do the what if again. Looks like that changed a lot. About 1.9. So it's somewhere in that range. So what you see me go through here, while it is, again, trial and error and iterative, it's very fast. Many companies, many product development groups, when they go through this, they do it in reality. They do it in the physical system over and over and over, build, test, fix, and spend an inordinate amount of time doing in the physical system what I've done here in simulation in a very short amount of time. Of course, always realize that this is nothing more than simulation of mathematical models and so on, and so you must go back to the physical system and set it up the way the simulation predicts, and confirm that you get the performance in the real system that the simulation is predicting. So you may want to increase capability a little bit, get it right on 2, or say I'm close enough now, given my capability of 1.9 and my mean temperature, mean cool time of 1.9 something. I'm tempted a little bit to increase this, decrease this number a little bit, slow the speed of the fan down a little bit, but I'm so close it's not worth doing. If I go back into the PowerPoint, you can see some of the screenshots here from At Risk, and I went through, actually these were to be hidden slides, but this is what we went through in the Excel spreadsheet and arrived at speed values, temperature values, and also volume values. We've achieved our CPK of 2. That's a 6 sigma performing system. We would expect associated with that for every million times we cool the system, about 3 or 4 of those times the cool time would be outside the spec limit, either above or below, most likely, well, leave it at that, either above or below. If I go back into the spreadsheet, let me run this again. Actually, I can bring it up from here. I can bring up the last graph. What I can do as well is put in my lower spec limit and put in my upper spec limit, and I get an estimate of the area inside the curve, the area of the curve inside the spec limits, let's say. And here it's not truly 100%, with no zeros after that, but it's very small. It's the most likely the 6 sigma performance of 3.4 ppm. And we can do a number of what ifs with this as well. What if our spec limits were narrower, 1.5 to 2.5, well below 6 sigma performance now. If those were our spec limits, 99.8% of the time we would be within the required cool time, but 0.2% of the time we we would not. And obviously 0.2% failure or out-of-spec performance is astronomical compared to Six Sigma performance. So back into the PowerPoint. Of course, confirmation, I had talked about that. And we confirm similarly to the way we confirmed earlier, set the system up to the way this is predicting, measure the response several times of the physical system, calculate a confidence interval, and compare the predicted from the simulation value to the confidence interval, and if all is well, that predicted value should be inside the confidence interval. What I've taken you through here is documented, captured in a text that I am co-author of, and so if anyone has this book, you can go through much of this in that book as well. And in this example, we're using at risk. So I think I will return control, or you take control, Jameson?
Well, that was wonderful. Thank you very much. I'm going to see if we have any questions. You can keep whatever you want on the screen. I'll leave control to you, and we'll
okay.
And see if maybe I'm looking at our question panel here. Wait a minute, maybe a question will come in. Everybody's welcome to submit a question.
Perhaps I've either put all to sleep or
no.
or maybe I explained it thoroughly, perhaps.
I do have a question, just came in.
Oh, okay.
Here's one. Nice presentation. I wonder if there might be an application for Risk Optimizer as an alternative to your what-if approach.
I imagine there is. I mean, the ideal flow would be that the values that the Risk Optimizer predicts are the ones you end up with. But keep in mind that the value, I suppose I could have optimized on mean and variance, mean and standard deviation concurrently for that one response, and then use those two numbers as the parameters of the statistics for each X, speed and temperature and so on. Perhaps that's where the questioner is headed. I'm not sure.
I've got another one. What happens if we don't know time-zero physical transfer function?
Please repeat, Jameson.
Sure. What happens if we don't know time-zero physical transfer function?
I'm not sure what you mean by time zero. Whether you mean initial conditions or you mean at the beginning of the development effort by time zero. But if you do not have a transfer function, if you do not have an equation, either from first principles of physics or from behavior through a design experiment, you may be able to create a CAD type of model of the system, a finite element analysis, or MATLAB, or some CAD tool that lets you build the system, simulate it, but without having the transfer functions. At risk can then parameterize those CAD tools and take the numbers that those CAD tool produces and do the Monte Carlo, do the optimization as though it were an equation in Excel. Is that getting at the heart of your question?
Oh, let's see. Well, I'll wait for our attendee to. Yes, the answer is yes. Thank you.
Okay, thank you. Yeah, good question, because you know, how often do we have these questions? These transfer functions, you know, for very complicated systems. The example here is that of a small piece of a much larger system, and that narrower scope, you know, let me come up with a transfer function from first principles of physics.
Great. Now I have another question, and I'm going to add to it. How was it done before the advent of at-risk, and how do you find our software better than how it was done before?
Well, before, obviously there was the by hand approach. I'm 53 years old, so I remember doing partial derivatives and so on, and first derivatives of the partials and so on. Tedious, laborious, error-prone. Alternative to that before these tools was trial and error, which unfortunately is still tremendously greatly in use. But build, test, fix, make the changes, build it, try it, make the changes, build it, try it, until either you get it right or the time and money runs out. So I would say those were the two major methods. The latter one, the build, test, fix, still being used quite a bit before we had these simulation tools.
Great. Oh, I have another one. Looking at your x variables for the transfer function, is the nonlinear nature of the input data a concern in the regression result?
No. The analytic technique, the regression equation, is quite capable of estimating nonlinear terms, squared terms in this case, as long as the experiment that generated the data had the ability, and by that I mean degrees of freedom, had the ability to estimate those quadratic effects. So no concern about a transfer function with squared terms in it, nonlinear terms in it.
Can you explain what the capability measurement metric is? I
believe so. In this case, I'm using a particular capability metric called CPK. The C stands for capability. The little p stands for process. So it's process capability, and the K indicates that not only are we interested in the variation in the response with regard to the spec limits, but we're interested in the average value of the response in regard to the spec limits. So this metric combines essentially measuring the distance of the mean of the response from the spec limits, as well as the variation in the response, the tails anyway, from the spec limit. So it's getting at what area, how much of that distribution of the response is beyond the upper and lower spec limits. And if you know the structure of that distribution, if you know it's normal or whatever the distribution is, you can then translate that area under the curve outside the upper and lower spec limit. You can convert it to parts per million outside the spec limit. Is that adequate answer?
Actually, I'd like Steve to ask you a couple questions.
No. Keep on going with the other questions.
Okay, good. We do have more questions.
Okay.
Questions aren't important.
Okay. Well, I think they are, but we'll go through these first, and because we do have a lot of questions. This is great. Did this approach eventually result in a cost saving?
Yes, undoubtedly compared to the way developers have approached previously. Again, it was primarily the build, test, fix approach, which can be a very time-consuming process. So the money saved, time saved, it's not like a Six Sigma project where a machine is stamping out 10 units a second or a minute, whatever, and through application of some of these tools, you have it now stamp out 20 a minute. You know, that increase is easy to observe, easy to measure, and easy to quantify in dollars. So the savings here, I suppose, probably is more like cost avoidance. So the avoiding the cost of the build, test, fix, multiple iterations that we probably would have gone through otherwise, you know, if we did not have these tools. Another area, and it wasn't the case so much in this, but another area of opportunity for savings, which is more easily calculated, would be in playing with the, and I use the term play pretty much literally, you know, in the simulation here, playing with the simulation to have the spec limit, to have the variation of the x's as wide as possible and still produce a response that's on target and capable. Almost always the wider the variation allowed or tolerated, the cheaper the part or the you know, the system is to produce, to procure, to maintain.
I've got more. Here we go. Build, test, fix is really build, run, DOE now, right? Is the central composite the best DOE for that curvature effect?
Well, I suppose you could do better. There are other types of DOEs. There's optimal DOEs, D-optimal, H-optimal, and so on. I would say out of the somewhat generic toolbox of DOE types that the DFSS black belt, the Six Sigma black belt is given, in this case that is probably the best DOE, yes, because we needed to estimate linear, quadratic, and two-way interacting action terms, and that is what the central composite design is primarily built for. So I'm sure with some fancy DOEs you could do better. I don't know that the amount by which you would do better would be worth it. Whoever asked that, what would you suggest as an alternative?
Well, there's another part to this question, maybe that'll help. Do you
Okay.
like a composite with inner axial points or exterior axial points? That is 0.66 or 1.6 axial points.
Exterior, outside the cube. So it was a sphere outside the cube of the central part. And so not face-centered, right?
Well, great. Here's another one. Have you found management receptive to the use of simulation approaches, or do they ever view it as somehow experimental?
Well, I found functional managers not my experience has been not resistive to the use of these tools. Higher up, though, management at a higher level, first of all, may not even see these kinds of activities and tools being used just because of their level in the project or in the corporation. But the bigger resistance, the bigger oversight is when you are deploying this as part of a much larger Design for Six Sigma deployment effort. That's where teams of people are being affected in terms of how they do their work, and that becomes visible to the project manager, to the program director, a few layers up. Yeah, I mean, if you need to do this and you don't have a transfer function and you need some extremely expensive finite element CAD tool, you might find resistance at the functional level for spending the money. But hopefully the functional managers are knowledgeable in engineering practices and understand the value of this and the savings.
I've got some more, if that's no trouble.
Well, I do have to break it off soon. I have a meeting I have to get to. But
okay. Well, there are a lot more questions, but I'm going to...
I take one more, but perhaps if it you can maybe send me maybe email with me the questions and who they are from, and I can individually, or email my responses to you, Jameson, and then maybe you collectively send it out to the attendees.
That would be wonderful. I think we'll do that. And
okay, because I apologize. I do not want to cut off anyone's questions, but I don't have a whole lot of time. So let's take one more, and then please do that, and I'll respond to all of them and email back to you, Jamison.
This is a good one, and I'd like to ask it just for many of us in attendance. Are the random numbers produced from at-risk or from Excel itself?
Oh, from at-risk. At-risk has, I really don't know the internals of at-risk. The algorithms for randomly selecting numbers from different distributions, maybe Jamison or Steve or one of the application engineers could help. But certainly it is coming from algorithms with inside at-risk and not from Excel.
Great. And what I'm going to do is everybody, if you wouldn't mind, email me your questions and any more, and I'll forward them to Jeff. And I'd like to thank everybody. I also want you to, when we shut off this webinar, I want you to see where we go. We're going to go to our Six Sigma page on our website. And I want to encourage you to download some free trial versions of our software. And I want to thank everybody. And this concludes our webinar today. Thank you for attending.
Thank you, everyone. Thank you very much. I appreciate your attendance. I look forward to your questions.
Thank you, Jeff.